Welcome to another Cosmology Talk. This week we have Hamsa Padmanabhan, who is a CETA Fellow, the Canadian Institute of Astrophysics, and an Associate at Dunlap. She's an expert on the H1 halo model, as well as 21 intensity mapping and generally just how hydrogen arranges itself inside galaxies. The specific reason that I invited her this week is that in a talk from about a month ago by Ulrich Bauer on a paper in which she's a co-author, it became very clear that a lot of the results that in that work, which was on how intensity mapping will be able to constrain axion models of dark matter, it became very clear that a lot of that work relied quite heavily on Hamsa's work on this H1 halo model. So given that I didn't have that much knowledge myself of the H1 halo model and Ulrich was talking about other stuff, it seemed a very good idea to bring her on to fill in all those gaps. So I promised in last week's talk that this wouldn't become an H0 channel. So I have fulfilled that promise, and this week we won't be talking about H0 at all. We'll be talking about H1 and perhaps even a little bit of H2. But yeah, in general, if 21 centimeter intensity mapping is to reach its full potential, it's the work of people like Hamsa that will bring it to that potential. So thanks, Hamsa, for joining us. Do you want to briefly summarize what it is that you do in the paper that you'll be talking about, and maybe also how it relates to your work with Ulrich?
Great, thank you so much. And so this paper and more generally my work on a 21 centimeter and neutral hydrogen is based on empirically modeling baryonic gas. So this is very relevant today, not only because baryonic gas remains our chief probe of the large-scale structure of the universe, more so during exciting epochs like reionization and the cosmic dawn, which are right on the brink of being observed by future generation telescopes, but also because right now it holds the clue to getting from the galaxy surveys, which are exploring at the moment a very small volume of the observable universe, to the CMB, which is out there, which is like, just one surface out there, a very small number of modes and just one surface. So all this intervening area, actually all this volume of this universe is accessible to us in baryonic gas, most of which is invisible because it's the dark ages and it's kind of the time when you don't have star formation and you just have hydrogen, helium, and structures collapsing. So in the light of what's going to come with, for example, big international efforts, SKA, and similar such efforts in molecular gas, it's a very good idea to ask ourselves, where do we stand in baryonic gas today? Yeah. What kind of story does today's data tell us, which we can kind of use as a stepping stone to understand future observations and predict, for example, cosmological forecasts, such as the ones even from for exotic stuff, axion dark matter, like you had in one of the previous cosmology talks, and various other things, maybe even primordial non-Gaussianity and other things.
Cool. So if someone's remembering this talk a couple of months from now, or they've read your paper and they're thinking back to what was in it, what would be two simple things that you'd want them to be remembering, 3 or 4 months from now, if that's all they remember?
So I think the first simple thing, which I would really call the key of all this effort and this empirical modeling and looking forward to the next generation surveys, is that it is possible to develop a data-driven analytical framework to understand baryonic gas, most notably neutral hydrogen, but also molecular hydrogen and carbon monoxide, which are related to star formation, and other tracers, which can be done with a minimalistic, statistically data-driven model, which is constrainable with basically a 5 or 4 parameter framework. Even though baryonic gas seems like, it's complicated. It has details in it. There are processes and physics, which is kind of, not very well understood, especially on smallest scales. Yeah. The interesting thing is there are a few free parameters that capture dominant processes. Okay. And thus bring it almost to the level of the standard lambda CDM, which is extremely simple and extremely well modeled. in the sense of modeling for these kind of experiments. So it kind of gives you a really good kind of understanding of processes, the cheap ones. And the second important thing is related to what I said a few minutes ago, which is that it has enormous implications and connections. It's extraordinarily malleable, ductile, and flexible. The very fact that you can make up a Halo model framework and that you can use it and constrain it with present day data tells you that you can basically forecast not just standard cosmological parameters from the next generation surveys, such as the ones with the SKA and its precursors, and lots of other efforts happening around the world.
Yep.
It also tells you that you can go one step beyond and look at non-standard cosmology and exotic scenarios. And really, this framework makes it flexible to do both these things. So these are the kind of things which I think are important about this empirical model.
Cool. So you've kind of justified a lot of what the next question we'll be asking already, but why did you do this? So but perhaps now on a more sort of specific level, not why 21 centimeters, but why the specific work. What questions were unsolved that you wanted to solve, and why were they unsolved? That sort of framing.
Just in a nutshell,
yeah.
It was very clear that there is a lot of data on baryonic gas, which we have right now, even today, even though our surveys have not reached the kind of scales which we are going to reach in a few years or decades. And the interesting thing was, even though there existed different data sets, by data sets, I mean different observational probes of molecular and atomic gas. For example, there are probes like the damped Lyman alpha systems, the DLAs, which are line of sight measurements, and there are galaxy surveys and intensity mapping also. It was very interesting that there wasn't a comprehensive framework in place which took all this different set of data and asked what the data can tell us about the evolution of gas in halos.
Okay.
What became very clear when we started on this is that when we look at it holistically across the entire part of the universe where we do have the data, we actually end up with extremely tight constraints on the Halo model framework, which were better than we ever expected. And this reason for the tightness was because of the holistic nature of the framework. So that was the first thing. And the second thing was there are a lot of quote unquote unsolved problems in the cosmological history of star formation and the buildup of material like molecular and atomic gas and its relation to the global sort of fueling of stars and the buildup of SFR, the star formation rate, which has been extremely well modeled for decades now. And while the stellar had been done extremely well, and the stellar had been sort of, and there's also a lot of surveys on the stellar component. There are HOD models, there's abundance matching, there's all these things. However, the similar treatment had not been done for gas as far as we could see because they hadn't been comprehensive at that. So this particular paper, this latest paper, basically focuses on kind of bringing together the now fully developed gas models with the existing stellar models so that you can comprehensively ask the question, how does star formation evolve and proceed, and what's the fuel and other things like that.
Cool. So let's dive into the details. If you want to bring up slides and things, what was it you did in the paper?
So like I said, I'm theming this around the latest paper, which is about the combination, like I said, of the different models and seeing what it means for star formation and its evolution. And I'm going to start with just telling you that everything here is more or less centered around this innovative technique known as intensity mapping, which many of us are familiar with, which in fact, Jurek said something about during his talk as well, and it's been gaining a lot of attention. over the last few years, and in fact over the last decade. So that basically what intensity mapping is that you essentially don't look at individual objects, such as the one on the top left panel. The top left panel is just showing you some galaxies which are selected in CO in a survey with VLA. But instead of going after each of these individual systems, you actually go to the integrated emission of the light rather than the individual things. And what is nice about intensity mapping is, as you could have guessed, it's much faster and much cheaper to do this rather than to go after each of these systems. So it allows you to prove these vast scales in the universe very well. And interestingly, it's also true that it can be done for different lines, for different traces of large scale structure, such as 21 centimeter, which is like the favorite line today for the purposes of cosmology and reionization and things. But also other lines like carbon monoxide and C+, which are very important traces of star formation in galaxies, which in turn ties into this 21 centimeter larger scales and things. The one thing which we need to keep in mind when we're looking at 21 centimeter or any of these intensity mapping is that astrophysics has a huge role to play, as one may have again guessed. And the way it comes in is that what you actually go after in an intensity mapping experiment is the power spectrum of the fluctuation. So that's what I show in the first formula here. The details are not very important at all. It's just that this is like your CMB fluctuation power spectrum. It's just, you know, at different scales K and different redshifts, you have this fluctuation square. And this quantity is made up of two salient parts. The first part is inherently cosmological. So for example, if you want to use intensity mapping to think about H naught or something like how the universe is expanding with time, you would be really focused on asking how do the pink quantities change with time. But you have to remember that the red quantities, which are related to H1, so this is just some abundance of H1, or like omega H1 is just measuring for you how much of it is there, just like omega matter, and VH1 is called the bias. So these kind of parameters interfere with the cosmological ones. So there's an interplay, and this leads to what we would call the astrophysical systematic in these kinds of surveys. Astrophysical systematic is actually something pretty simple when we think about it. Essentially, we know that we have a smooth cosmological background. So in the sense that most of our current surveys have told us that cosmological parameters are fairly well known, fairly precisely measured, maybe a few percent, even sub% in many cases. But when we do intensity mapping, we need to keep in mind that we are looking at this nice cosmological background through the lens of astrophysical uncertainty. And practically every single one of these traces brings with it its own astrophysics. So this needs to be quantified. And this is something we started looking at with Alex Refrigier and Tirth Chowdhury in 2014-15, when we were looking at basically how much does the uncertainty in the astrophysics propagate into the power spectrum of 21 centimeter intensity fluctuations. So this graph is just indicative. It's telling you about how much, for example, our constraints on omega H1 are sort of span out over time, over redshift. And you can see that it's pretty big. I mean, the kind of uncertainty we have in this astrophysics apparently leads to 60 to 100% uncertainty in the power spectrum, which if you just simply propagate, yeah.
And this is as measured
This
at
is
these ridges.
precisely measured, yes.
And
So
how
what
does
we
one measure omega H1? Just by...
Correct. So different techniques are used at different redshifts. So
Okay.
for at low redshifts, there are galaxy surveys, and at higher redshifts, there are these damped Lyman alpha systems, both of which I'll describe a bit more in the next few slides.
Okay.
And the cool thing, the interesting thing about this is that actually it's pretty high. It's not as low as one would have thought. So it can have an effect. And we need to quantify this effect by efficiently modeling this astrophysics. So that serves two sort of goals. The first thing is you can model the astrophysics and take it out for cosmology. And the second thing is that you can actually understand the astrophysics and connect it up with other astrophysical constraints. And the most natural way to do this seems to be by using a Helomotor framework, which is the subject of most of the papers which we talked about before. And this is basically introducing for you what the Helomotor framework does. Essentially, it combines the intensity mapping with individual objects. So you have all these different kinds of observations and you want to combine them. And what can be shown, which we did in this paper, is that there are essentially two salient ingredients in a Helomotor framework for associating baryonic gas with dark matter halos. So the first one is the average mass of H1. So here it's H1, but it could be anything. It could be, for example, CO luminosity or H2 mass associated with a halo of mass M and at redshift of Z. And the second ingredient is the way this distribution is profiled. Just as you do for dark matter, you have NFW kind of profiles and things. So it turns out that if you want to make halo models for baryonic gas, you need this profile and you need this H1 average mass in a halo. And what is...
And presumably when doing any final analysis, do you allow scatter around the... Yep, yeah. Okay.
So most of the times, definitely, yes. Most of the times it's easier to do it when you do with abundance matching techniques, which is the subject of one of the later papers which we wrote. This, right now, the two things I'm telling you are just averages, but definitely when you introduce scatter, you see basically how much of a leeway you have in each of these quantities. Right. So the way you model this for the case of H1 is interesting, and I just will point out the important features of the framework. The first ingredient, the H1 to halo mass, is modeled with three free parameters. So the first is called alpha, and this alpha measures the fraction of H1 relative to the cosmic fraction. The cosmic fraction is FHC, which is basically just dependent on the helium part and omega baryon and omega matter. Whereas that's just telling you how much it would be if it was the cosmological one. But alpha allows you to kind of go up and down with respect to that. So it's a free parameter.
So it's the fraction of H1, of the total amount of H1, it's the fraction that is in a halo rather than just like diffuse?
Precisely, yes. The second parameter is called the slope, and you can see that what it's doing for you is to tell you that H1 mass need not be proportional to halo mass. So you see that an extra beta parameter is needed to just quantify deviations from unity slope, unity between the H1 mass and halo mass. And the third parameter is called VC0. You can see that on the exponential. And VC0 is an interesting parameter because it tells you, it basically gives you a sense of how small a halo has to be for it not to preferentially host H1. So basically, this cuts you off. It's a lower cutoff, and you can do a cutoff in terms of mass, but it's physically more natural to do it in terms of virial velocity, which also connects up to some very interesting analytical arguments, which I will have probably a minute to talk about later.
Okay.
And you had a question?
Yeah, I mean, it sounds like you might be planning to answer one of the questions later. I guess power laws are like the first thing to go to when you're deviating from a linear relationship. But is there a good kind of modeling or theoretical reason why one would expect that the dependence of MH1 on M can be just a simple power law? Or is that sort of just the first thing to go to?
So there are actually two answers to this. The first is that actually in the literature, when people did modeling of the H1 system, especially the PLAs and so on, people found that it's either linear or sort of like a power law from the results of simulations, from observations, and so on. The second, and in my opinion, more important reason is that we found, which I will, again, it will come in the next couple of slides, that this is the statistically most favored evidence-wise and Occam's razor-wise model, which uses all the data, and there is the introduction of more parameters into the beta, especially into the beta and the VC0, is not warranted at this stage with our present data. So
it's a little bit motivated from simulation, but a lot motivated from empirical matching to observations.
It's precise, exactly that. Because we try, for example, we tried different combinations and different sort of physically motivated models, and we found that the one which had this 5-parameter nice framework was surprisingly, pleasantly surprised that it was basically the one which was best matched to the combination of all the data we have. So yeah, that is indeed one of the takeaways, and so it continues to be something which I think is telling us something deeper about baryonic gas. Right, so the profile again is pretty well modeled, just like we do for the dark matter. So what you see here is an exponential kind of profile, and which has a scale radius which depends on what we would call a concentration parameter. And the concentration parameter basically has two different free parameters in it, one of them being just a normalization, and the other one being something which tells you how this evolves with redshift. And most of the motivation again for this kind of form is that most studies, this is why I've quoted some of them in the reference there, they find that the profile of H1 is very close to surface exponential. Surface exponential is not quite a radial exponential, it's more a K0 Bessel, but for all practical purposes, a radial exponential works very well.
What does surface exponential mean as a technical term?
So what I mean is that when people look at images of galaxies in H1, the surface densities are exponential, not necessarily the radial densities.
So the surface being the thing you see, not the actual physical radius. So I guess there are again two kind of maybe additional questions to that. Is I guess you've got a dependence on the mass that is to the power of minus 0.109.
That one is, I was absolutely going to come to that. Absolutely ignore that, because that is just inherited from the dark matter. It doesn't do anything. It's just there because it was basically a result of several fits to simulations. And the power is so negligibly small that it doesn't really do it.
And then there's the 1 plus z to the gamma.
That's right. Gamma is important.
That's again a sort of power law with redshift. Is that motivated by simulation, empirical data? Is there some theory that one can motivate that with?
So again, what was interesting about this gamma is that originally people did not even put a gamma. So it was basically, as you might have recognized, the formula here is identical to the one for dark matter, except for the H1 subscripts in there, for the CH1, for example, except that it also doesn't have a gamma. It'll just have 1 plus z in it. However, what we found again is that trying to evolve this for the case of H1 necessitated something which we would like to do with redshift, especially since we need to also think about how this virial velocity with redshift relation is influencing the H1 to halo mass relation. That's why one of the simplest, again, it's Occam's razor, it's statistically simplest to add in a gamma as a power law, which could be 0, for example, or which could be 1, which was the dark matter case.
Mm-hmm.
So it allowed us to basically explore every scenario which was reasonable. So this is, again, coming back to one of the questions you asked. So you have the different kinds of data which constrain the H1, and this is what we matched the Helomotor framework to, basically. This and a few more, but this is just a glimpse. The first thing you would notice is that the data kind of divide themselves into 3 classes. The 3 classes are essentially, very broadly speaking, again, emission line surveys in 21 centimeters. So what this is doing for you is that you have normal galaxy surveys, like you have an optical, those kind of surveys are there in 21 centimeter. Mm-hmm. And these are some examples of that. There is also an intensity mapping survey. There's been a series of them conducted by people at CETA, Willie Penn and his group, Eric Schweitzer, which is the GBT2, happening around redshift between 0.6 and 1. So it's kind of in an intermediate redshift kind of regime. And very interestingly, there is a huge amount of data on neutral hydrogen, same systems, same kind of processes, which are available to us through their absorption. So this is the damp Lyman alpha absorption spectra of H1. And these are line of sight surveys. There are more than 30,000 right now and counting, SDSS and all these big surveys. And this is why the original point that all these different kinds of observations trace the same sort of systems, the same sort of H1 systems. It's not known yet whether the DLAs are proto-galaxies or they're actual galaxies. That's kind of unknown, but they're definitely the biggest reservoirs of neutral hydrogen between redshift 2 and 1.
So what does the damped part of the damped Lyman alpha mean?
So the damped part of the damped Lyman alpha really refers to the way the profile is shaped. So in the original, long back when people did not have the quantum mechanical theory, they were modeled akin to the damped harmonic oscillators.
I see.
And the way the Lorentzian, profile, the kind of, there are damping wings which show up in these profiles, which were, therefore the name stuck. And this damping part of the damped Lyman and the damped oscillator lends its name to the
but there's no there's no physics that's oscillating that's damping out or anything.
Oh, no. People thought it was the damped harmonic oscillator, which was the, and therefore they had this name, but then now we of course know that it's a Lorentzian. So what is now very interesting is that when you combine this 5-parameter framework with the all the data which is available to us in H1, which I showed in the previous slide, you get very, very nice constraints on these parameters, which was absolutely not something we expected out of the box. And we found that given that all these different observations are tracing different parts of the redshift regime, they came together to constrain these. This is using a Markov chain Monte Carlo, these baryonic gas parameters, these 5 parameters, to very reasonable accuracies. So just to remind you, the data is H1 galaxy, DLA, intensity mapping, and everything. And you can do it for different profiles. I'm just showing you the one for the exponential profile.
Okay.
And also, this revealed to us about the best fitting Helomotor framework, which was constrained by the combination of the data. And interestingly, it has 2 salient features. So the first one comes to the beta, which we discussed in some detail. You can see that there is evidence for beta. That's plotted on the left-hand side. The H1 mass to halo mass, and the linear is shown in the dashed line. So if beta had not been there, it should have been following the dashed line, but beta is there, and it seems to kind of suppress the H1 mass at high halo masses. The second thing is an exponential profile fits very well, and it has a sort of a nice scale radius where you'd expect it. Something like 20 kpc is where you would kind of, those are galactic scales. That's the kind of radius picked out by these profiles. And the concentration parameter is about 10 times of that of the halo dark matter. So that also fits with all the observations that you're going to have a scale radius, which is, for example, the number which you may be familiar with is something like 3.4 for dark matter, so that the total, the 3.4 times 4 is something like 10. What happens for H1, the corresponding number is like 28, which you can see in the first column in the right-hand side. And that's just telling you about this kind of few 10 kbc galactic scales.
And dark matter halos, I guess they're normally fitting to this NFW. This, I mean, when you just quoted numbers to me, is that from some literature I'm unaware of where they fit to an exponential profile as well? I guess that's passed me by, I guess.
Yeah, absolutely. I mean, whichever profile you choose, sort of you would get something like about 10 times less concentrated. And this is a really very, this is just broadly telling you that H1 is sensible. It's doing what we see. It's kind of concentrated in this heat, just like around 20 kpc scale length.
Okay.
And yeah, so I'll just quickly tell you, this is also going to connect to various questions we discussed in the last slides, but interestingly, this is not all statistics and no physics. There are a bunch of very interesting insights that we found we garner from the Helomotor framework, and which sort of connects very beautifully to various physical processes which people have studied in the literature before. So to do that, let's just quickly look at this relation again. We have the three free parameters of the H1 to halo mass relation. And essentially, each of them tells a story. So the first one, the alpha, basically tells you that the number is like 10%. And this tells you that basically alpha is, you can see that the cold gas, which is on the which is plotted for several observations and simulations on the graph, is consistent with being between 10-20% of the total cosmic fraction. So that is essentially what alpha is doing for you, and it ties in with these observations as well. Okay. Interestingly, alpha doesn't depend on Z. We tried different, as we said, we tried different parameterizations, and the MCMC stubbornly refused to allow variation with Z given the current data. That has a nice physical interpretation, because apparently this has been actually postulated, observed in the literature before on the non-evolution. So this is something people had been studying since 2008 and so. And this kind of ties in H1 accretion and consumption. So basically, there is an argument which is that H1 accreted from the IgM is also consumed when it goes into star formation. So there's a nice
I see.
Back and forth. Yeah. Beta is called the slope, and beta basically, as we know, basically shows you how this is sloped with respect to the H1 to halo mass. And interestingly, the beta has a bit of history. Like there was 21 centimeter based models, which are shown. There's this model which is shown as the hump, and there were also DLA based models, which were in the past. There were different kinds of models people used, and interestingly, they're so different from each other. So they were used to model these different parts of parameter space, of the redshift space. And in one of the previous studies, what we thought we would do is that we would take these models and just fit the observations by combining the models at face value without doing any tweaking to the models. And what we found is that actually a model which combines these two older sort of predictions fitted most of the data, but it did a bad job at fitting the H1 mass function. You can see on the right-hand side. You can see that most of the H1 mass function at high masses is over-predicted. And the MCMC told us that the beta parameter actually solves that problem. And the reason why we did not have this match before was because all previous models assumed beta of 1.
Mm-hmm.
So within scatter, it fits almost perfectly. And you find that basically the beta is needed for fitting this observation. So that was very interesting. And it's related to what people would call quenching and feedback at the high mass end for physical. The third one actually is the most interesting of all, and the number you get for, and this tells you about, as I said, the lower cutoff of the halos which can't host the H1. What is interesting about this number is that it goes to something like 36.3 kilometers per second. Okay. This seems to be, I mean, as a number, one probably doesn't have much much feel for this, but interestingly, when you consider what this is related to. So for example, long time ago, right from 86 and other 92 and so on, people had been looking at dwarf galaxy formation. And there'd been analytical arguments, Rees and Efstathiou and other authors, where they basically asked how small should a galaxy be so that the photoionization, which increases cooling time scales, suppresses the formation of dwarf galaxies. Very interestingly, their analytical arguments with the current then available UV parameters and galaxy parameters favored 37 kilometers per second.
Okay.
So it's amazing that 2017 favors 36.3, which is really telling you that this process of photoionization cooling seems to be the dominant one driving the accretion and the H1 gas in low mass halos. So yeah, because this is a cosmology talk, I thought I would include one slide on the kind of interesting cosmology you can do with it. And one of them, of course, is axion, dark matter, and the other kinds of exotic probes. What we explore in some of these papers is to constrain standard cosmological parameters, that's the left-hand side, top panel, by using a Fisher forecasting formalism with this Helomotor framework. We also look at cross correlations between galaxy surveys and 21 centimeter surveys, as shown on the second figure on the top panel. And recently, we also looked at whether you can constrain effects on ultra large scales like primordial non-Gaussianity, and whether the bias on these kind of parameters would be affected by the inclusion of astrophysics. Happily, for primordial non-Gaussianity, that turns out not to be the case.
Cool.
So that's some of the things you could do. What you can also do is to do the same thing for carbon monoxide, which is what I do in this paper. I take constraints between redshift 0 to 3 in CO and combine them to a Helomotor framework. And in so doing, you get constraints combining the individual CO objects and the intensity mapping constraints with parametrization, which is very similar to the one we use for star formation. So this is something which is, again, physically motivated. And what I find is that you can match most of the data we already have. CO is not as well measured as H1 thus far, but by redshift 0 to 3, we have pretty good constraints. And what the lower panel is showing you is that basically you can do interesting things for predicting the power spectrum of CO fluctuations, which are measurable by current and future surveys.
So with carbon monoxide, I feel immediately that either I have a misconception, or it seems like it must be less constraining of cosmology, because the hydrogen that's there is left over from nuclear synthesis, right? Like it's just, whereas there was no carbon monoxide made in nuclear synthesis. So any carbon monoxide that exists must have already been through all sorts of messy astrophysical things. But does it kind of equilibrate enough that you still expect it to trace the dark matter distribution, or is it not doing that?
So you're absolutely right that hydrogen is much more primeval compared to carbon monoxide and C+ and things like that. It's found that hydrogen is definitely needed to trace, like if you want to do ultra large scales with FNLs and axions and things like that, you would go with centimeter. What is interesting about CO happens to be that it is very tightly related to star formation, and it's always located, primarily it's located inside galaxies. That's why it's used as a, I would think that the tracer, the fact that CO traces halos comes from the fact that it's inside the galaxy itself, and the galaxy is tracing the halo through star formation and things like this.
Okay, okay.
So that's why CO is interesting.
And then can CO inside the galaxy be better measured than hydrogen inside the galaxy, or?
Very much so, exactly.
Okay,
And
okay.
for various reasons, people are interested. For example, in the future, there are surveys. One of the surveys I'm involved in is COMAP, which is led out of Caltech and is kind of trying to measure the CO between redshift 2 and 3.
Mm-hmm.
And therefore, it's easier, and it's also very easy from the ground, and foregrounds are less of an issue. So there are observational things which facilitate it.
Mm-hmm.
So yeah, so now I just come to the last couple of slides, which really come to how you bring all these different techniques together.
Okay.
And the first thing to note is that when you take H1 and you use the already existing star formation constraints, then you can basically plot H1 versus stellar mass. Mm-hmm. That's something which we do on the slide on the left. This is what we do is you take the H1 constraints from abundance matching of the H1 mass function to the dark matter halos. So that's kind of like a reverse engineering. And what you find is those constraints are very similar to the ones we obtained the halo model. So it all ties in together. What is nice is the same thing has been done for stellar evolution already and has been sort of presented to us. And that's the work by Moster et al., Beruzzi et al., which is also ongoing. Okay. Because like I said in the very early slides, stellar evolution is extremely well constrained. Mm-hmm. So now we have a way to basically connect the baryonic gas, which is the fuel for star formation, with star formation and stars themselves. So this is also shown in the right-hand side, which is the latest paper, where we look at this kind of evolution across redshifts. So you take the H1 halo model, and you take the already existing stellar to halo mass relations, which are available, and you just find out how these different quantities evolve with halo mass and with redshift.
Okay.
So this tells you a bunch of interesting things. The first thing is that you can now model baryonic gas merger trees. You may have, of course, heard of the halo merger trees, which are like following halos across cosmic time and how they accrete and how they merge. All you need to do is to populate the halos with H1 according to the prescription with CO and assume a CO to H2 conversion factor, which is quite well understood in the literature, though its details are not understood, like its value across redshifts. But you have here a way to get the H1 and H2 mass, which is shown in the orange, and the stellar mass shown in the blue, at different halo masses across cosmic time. So you can do that. This shows you basically the baryonic buildups. Interestingly, it shows you that 10 to the 12 halos, which are the second panel, are very efficient, the most efficient, the Milky Way sized ones at converting the gas to stars. So that is quite interesting. And it also, you can do what is like, you can basically do the derivative, logarithmic derivative basically, which is on the second half of the slide, of each of these components. So you ask, how does the H1 mass, stellar mass, halo mass, for example, evolve across cosmic time? An extremely interesting, as yet unsolved problem in stellar evolution as well as in cosmological star formation is that, like I said in one of the very early slides, H1 is pretty constant across redshifts at 0.09. Omega H1 is kind of constant. But stars are going all over the place. Star formation rates are going up and going down. Okay. And how does that happen? You know, what is the kind of, I mean, is there a simple way of understanding? One of the chief insights which we found in this paper is that actually this happens because stellar mass is very closely linked to the H2 mass rather than the H1 mass. You see that H1 is an intermediary. It's kind of a non-player, as you can see in as the orange line. The stellar mass follows the H2 mass at early times, which points to smooth accretion being the dominant mode of buildup of stars. Whereas, as you can see at the late times, it actually straddles the halo mass. So telling you that mergers seem to be the most efficient way of getting to stars, forming stars at late times. Both of these are very consistent with the results of simulations and analytical arguments.
Why did the fact that the stellar mass followed the H2 mass at early times, why did that mean it was like smooth accretion? Or is it just that it's following a diffuse gaseous background that means it's...
Exactly.
Okay, I thought it was because it was H2 rather than H1, but it's because it's H2 rather than halo mass.
Exactly. And there are other details in our paper that you would see that the way star formation rate proceeds closely straddles the way molecular hydrogen proceeds. Remember that the molecular hydrogen is coming from some intensity mapping observations of CO and some other, surveys. So that really told us that everything is connected, that the loops are being closed in a very interesting way. So that's it. Let me just quickly summarize by telling you that you need an accurate understanding of the astrophysics to look at the baryonic universe with intensity mapping, which is both a blessing and a curse because it kind of interplays with your cosmology. And the most natural way one can think of quantifying this is by using a data-driven Helomotor framework, which we've been looking at over the years. And it seems to really give us a lot more than what we put in the sense that it is really flexible and can explore the impact of astrophysics on these interesting forecasts, on the precision and accuracy. We didn't get too much to that, but you can do FNL and you can do a lot of interesting other things in cosmologically. And also you can do cross correlations, which are becoming very important today with galaxy surveys. And extend this to other tracers, like we saw that it could be extended to the CO and the C plus also, which we didn't see, but molecular hydrogen and so on, which finally enables you to connect baryonic gas, molecular and atomic gas, with star formation history and stellar mass. So that really ties up a lot of interconnected topics. So,
I guess there's a question that I guess maybe always gets asked at this point, but if one is trying to constrain cosmology, is it ever possible to know the difference between some new cosmological effect or some astrophysical effect that is a deviation from the halo model? How do you know the difference between it's not a power law, you need to go to the next order of expansion in that, to, I don't know, W is not equaling -1 or something like that? That's not to say that what you're doing doesn't have obviously lots of useful insights and things, but is there like a way to overcome that problem?
I think for that, this is something we explored in some detail when we're doing this cross correlations paper, which again, we didn't have too much time to talk about here, but it's there in like DESI, etc. are important traces of galaxy surveys, and this is one of the ways you can combine. You can look at the degeneracy structure of the cosmology and astrophysics. And that's pretty revealing actually, because it shows you that certain kinds of parameters push the CL in certain ways. So what we basically do, we address this a lot in the two papers which we didn't have time to go into, which are the cosmological forecasts and the cross correlations. So you find that really the astrophysics does degrade cosmological forecasts, but you can get an understanding of how much it degrades and how basically you can overcome it by looking at the degeneracy structure and its evolution across spectrum. So I think that's a partial answer to your question, but really the data, I think the forthcoming data would hold a lot of promise to understand whether these degeneracies are an issue or they can be successfully mitigated.
Cool, thanks. So then I guess last proper question is where to now?
So the future holds a lot of promise. Like I said, the SPA is a big player in the history of neutral hydrogen reionization and other exciting things. And so is the CO map, which is a survey led out of Caltech and is taking data on star formation histories at redshifts 2 to 3, where the molecular and the atomic models are very interesting and useful. And what I think is also very important is that not only for understanding these different traces. For example, we now have data in C+, which is the singly ionized carbon, at redshifts of between 6 and 10. This is places which we haven't even crossed with neutral hydrogen. And we're seeing galaxies with ALMA and other telescopes. And what is very interesting is that these kind of frameworks, these Halo model and an empirical framework, it's importantly data-driven framework, holds a lot of promise for interpreting these distant observations. Because once we understand the way C+ traces large-scale structure, for example, or CO, then we would have a clue about how the 21 centimeter observations can give us more information. Like what kind of information should we look for? What kind of galaxies host gas? What kind of galaxies are important for star formation? So these are the questions which I think we're already answering, and we should be able to answer much better.
Cool, cool. And so yeah, the final question outside of your own research, what do you think is the most interesting thing in cosmology at the moment, or astrophysics if you want?
So I'm going to probably cheat for my answer to this a little bit, but you can tell me which of the two you would accept. So the first thing is that the problem which I think is really important and really exciting in cosmology, one of the chief ones is the cosmological constant problem. I happen to have worked on this a little bit from the emergent gravity paradigm and approaches to quantum gravity. You know, how you can propose a possible solution to the cosmological constant problem in the light of these theories. But so it's not exactly my research at the moment, but it's still something I have worked on. But if you would like to know the problem which I would consider most interesting and I have absolutely never worked on, it would be the problem of baryogenesis. I think that's a very beautiful and very interesting problem of cosmogenesis, really. How did all this come into the picture, for example? So next to the cosmological constant problem, I think this is really, really important. And this baryon, anti-baryon asymmetry, and so on. So,
I guess in the particle theory world, baryogenesis and leptogenesis, and I guess cosmogenesis is still something that's very actively worked on. But in the kind of cosmology sense, because no new observations are shedding, constant new light on it, it's kind of, a little bit, I wouldn't say neglected, but just like forgotten.
I mean, I think we already have, it just needs, I would think that I just need a breakthrough, a theoretical breakthrough. I mean, I think the answer lies somewhere in theory. So it's definitely something I would love to work on. Maybe it's connected to the nature of dark matter because these are kind of connected. So I think that's a really beautiful problem, and it's completely unknown. We don't know the answer.
Yeah, I guess the fact that the omega baryon and omega matter are so similar indicates also that maybe the dark matter genesis and baryogenesis are related. Because otherwise, why would they be so close? Unless there's some anthropic reason.
Yeah, I would probably not put too much weight on the anthropic thing, but that's just my personal opinion. I think it would be lovely to figure out why that little bit of baryons over antibaryons, and basically that led to everything.
Cool. Thanks everyone for watching. If you like this, please do subscribe, click the bell, tell your colleagues, all of that sort of stuff. And if you have any questions or suggestions, leave a comment, and I can make sure Hamsa sees them. While you're here, you should check out some other videos. Obviously, in the context of this video, you should check out Urek's talk, because he's talking about work he did with Hamsa using the H1 Halo model to constrain axion dark matter. And thanks again, Hamsa, for a really, really insightful talk.
Thank you very much, Sean.